Welcome to Presentation 13. Today I'm going to cover the electrically erasable, programmable, read-only memory, which is EEPROM. As usual, I start by showing you our architecture. In yellow is the item that we're going to talk about today, which is the EEPROM, and is part of our layer 2 architecture. The items in green are the ones that I've already presented. So the agenda for today will be as follows. I'm going to give you some background on the EEPROM. We're going to develop our framework, and then we're going to go through an example program. Now the microcontroller has a special memory called the EEPROM that can hold data permanently. That means that we can remove the power for the controller and then apply later, and we can access that data from the EEPROM. The total size of the EEPROM is 1024 bytes. The address range is between 0 and 1023 decimal, or between 0 and 3FF hexadecimal. User can access each bit individually. User has full control over when and how it can write or read from the EEPROM. Typically utilized for saving settings, calibration data parameters, or counters. Now, to perform the write, we have to go through the following steps. First, loading the address and data into the EEPROM registers. So first we load the address into the EEPROM address register, which is the EEAR. Next, we load the data into the data register, which is the EEDR. Next, to start the write process, we need to set 2 bits. The first one is the EEPROM master write enable, which is the EEMPE bit. Next, we have to set the EEPROM write enable, which is the EEPEE. That once we set the EEPE, the write process starts immediately. So we need to wait for completion. During this time, it is important not to start another write operation until the current one has finished. Now, for reading information from the EEPROM, the first step is to set the address in the EEPROM address register, which is the EEAR, which, by the way, is the same one we loaded the address for the writing. Next, to start the reading process, we need to set the EEPROM read enable bit, which starts the operation, which is the EERE. Now, once we set the read enable bit, the data from the memory will be loaded into the EEDR register, which is the EEPROM data register. So we need to get the data from this register and load it into one of our variables so we can use it. So now let's get to the next item in our agenda, which is the EEPROM framework. So first, we'll review our data sheet. Reviewing our data sheet is always important so we can see where the data came from and we can find any additional information. And after that, we'll just put together our framework. All the information we need for programming our microcontroller is contained in the data sheet. Now, this data sheet is organized by functionality. So let's go to the AVR memory. From here, let's jump to a register description. There are 7 registers here. We have 2 EEPROM address register. One is the register high and the next one is the register low. These 2 registers contain the address where we want to store our data or the address from where we want to read our data. Next we have the data register. This register will contain the data we want to store or the data we want to read. Next, we have the control register. By manipulating the bits in the control register, we can configure and control the EEPROM read and write function. For example, we have here the EEPROM master write enable or the interrupt enable. Next, we have 3 general purpose I/O registers. We can read or write from this register. So I think this gives you a global idea of what's contained on the data sheet and how to find it. So let's go and put together our framework. Okay, so this is the table that's going to help us put together the framework. So here we have the function names, which are basically the registers that we got from the data sheet. Next we have the bit of each of the registers and then the bit name. So based on this, we're going to write our code, which is right here, which is a number of defined code. So the framework will be implemented as an include file, which is going to be the framework EEPROM.h, and you can see here what's going to be contained on the framework. The source code is generated by extracting the contents from our column code. So all this came from our column code and we developed that based on the information from the data sheet. Now, to prevent any naming conflict with existing development environment, the parameter names have been modified by adding an X in the front. So each of the parameter, I place an X in the front, so we don't have a conflict with the development environment, because many of them, they already do this work for you. But some don't, so you need to know where things come from and if you have to do it or not. Now, as a side effect, we have created traceability for our source code back to the ATMEGA 328 datasheet. So let's continue with our sample program. So here we have a schematic. So we're going to have the ATMEGA 328 connected to a laptop serially, and we'll have a USB serial adapter to make that happen. So what is the program going to do? First, it's going to store data into the EEPROM. Next, it's going to read the stored data from the EEPROM. And finally, we are going to display the read data in a computer laptop using hyperterminal. So basically, we store data, then we are going to actually display the data that we stored. Next, we are going to get the data, and we're going to display the data that we got, and we're going to verify that both are the same, which verifies that we load data into the memory and we're able to access it. So what do we need to do? So we have two things to do. The first one is we need to write the program to be included for interfacing the computer with the terminal. So we're going to write a program that's going to enable us to write items into the laptop to be displayed. Next, we have to write the actual program to store and distribute the data from the EEPROM and display it. So first, we're going to write the program for the include. So before we do this, I'm going to give you a little bit of background on some C routines, because all the data that gets transferred between the microcontroller and the laptop has to be in ASCII value. So we're going to have to convert all our parameters to ASCII value and then transmit them. And C has a couple functions that will help us in doing that. So the first function is called the UTOA, and it's a function that converts unsigned integers to ASCII value. So let's see what the function looks like. So basically we write UTOA open parentheses, and then we have three parameters. One we're going to call enum. The other one is going to be str2, and the third parameter is going to be the base. The enum is the unsigned integer value to be converted to ASCII string, and the conversion result is going to be stored in the str2 array. So number is going to be converted and where it's going to be stored once it gets converted. Now the number will be represented in base 2, 8, 10, or 16. So basically the number that we put here in the base parameter is going to define how the data will be. The integer would be a representation of a base 2, 8, 10, or 16 number. So let's go through the example. If the enum is equal to 5 and the base is 2, then the resulting string stored in str2 will be 101, which is 5 in base 2. So let's look at, so this is the function that converts unsigned integers. So now let's look at the function that converts integers. So that would be the ITOA. It's a function that converts an integer to an ASCII string. So what does the line of code would look? So it would be, we would write ITOA open parentheses enum, comma, str2, comma, base. The enum is the integer value to be converted to ASCII string and stored in the str2 array. Now the number will be represented in base 2, 8, 10, or 16, same as before. So we put in the parameter base, we put in what base we want the ASCII value to be represented. So let's go through an example. So if our enum is 123 and we put a base 10, then the resulting string is which is stored in SDR2 would be just 123. So final function is going to be the one that is going to convert the floating point to an ASCII string. So that's the DTOSTRF function, and it's a function that converts floating point number into ASCII string. So this is what the line of code would look like. We would type DTOSTRF open parentheses. In this case, we have 4 parameters. The first one is the fnum, comma. Next one is num size, comma, fraction size, comma, STR1. So the fnum is the floating point number to be converted to the ASCII string and stored in STR1. The num size specifies the total width of the output, including the decimal points and the fractional digits. So how many fractions, how many numbers, how many digits your number has, or how many digits will be included in the number that is going to be converted to ASCII. The fraction size specifies the number of decimal after the decimal point. So let's go through the example. So let's assume we have an fnum of 3.14159 with a num size of 8 and a fraction size of 3. So then the resulting ASCII string would be the 3 plus we only have 3 fractions, so it would be 3.142. It would leave out the rest with the spaces on the left to make a total of 8 characters. So let's go to our sample program, and I'll explain how it's going to work. The purpose of this program is to convert the different types of numbers to ASCII character and to transfer those ASCII characters to a hyperterminal. Now, during my presentation 12, I explained how to configure the register to transfer serial data from the microcontroller to the hyperterminal located application in the laptop. So I am only going to discuss here the new items. Now the header in this here, what it does, it provides to the user the requirements to be able to use this program. So for example, it has the settings for the UART. That would be the baud rate, the data bit size, the stop bits, parity. It also states what needs to be included in that program. For example, it has to include the framework.h, framework ports, framework timers, framework UART, and finally this program, which is the framework UART routine rep A. So now let's start looking at the code. So here we have the init UART, which we already discussed in presentation 12, which basically it says all the parameters needed for the transmissions. Next we have the UART transmitter, which is basically the function that sends the data out. Next we have the transmit tab. That's a new command that I don't think we've seen before, and that's the hex 09. And what it does is every time you call it, it places a space, and the command to do that on the hyperterminal is hex 09. Next we have the command which says, the routine I should say, that says new line. And what this routine does, it sends the carriage return command, which is hex 0D, and the line feed command, which is hex 0A. What is that doing is sending the command to go to a new line. So if you need to go to a new line, you use the new line, and then the input would be how many lines you want to go down. So here we have the clear screen routine. We've seen this before, and it's basically the command that places that clears the screen and places the cursor on the top left corner. So that would be these two commands. Next, we have the parse string. The input is a pointer to a string. A way to look at this is by considering this to be an array of character, and the last character is the null. So we start here the while, and this while is going to keep going as long as you don't get to the null character. Now here we transmit each of the ASCII character, and then we go to the next one, and eventually we're going to get to the null character. When we get to the null character, then we jump to the next command line of code, which is the transmit tab, which puts a space. Next, we have the serial uint _2. This is the serial unsigned integer base 2. So you put a number enum, and what this does is we use the function ut0a to convert the number into a string in base 2, and then it gets transmitted by the parse string str2. Now the function serial integer _2 is similar, except that we use the itoa function to convert the number into a ASCII character string to be transmitted. Now we do the same for the base 10, which is exactly as we did for the unsigned base 2. So in this case, it's unsigned base 10, which again we use the UTOA to place the number has been converted to ASCII and placed on the STR2, and then we use the parse string. Then we do the same here for the base 10 but integer. Then we have 1 to do base 16 for the unsigned integer, and for the serial integer base 16. So this is basically the same, except that we put the value 16, so it gets converted to ASCII in the base 16, and then it gets transmitted using the parse string str2. And finally, here we have the serial float. Now this is going to use the DTOSTRF function, which basically converts the number, which is a floating number, and it places into the string 1. And as noted before, we have control over the size of the fraction and the size of the number, and using the parse string transmit the ASCII value that was converted by the DTOSTRF function. So this explains what going to be the purpose of this routine and the functionality. So let's continue to the main program. Okay, as I mentioned, let's let's continue developing our with the main program. So we wrote the program to do all the transfer between the ATMEGA 328 and the laptop. Now we have to write the program to store and retrieve data from the EEPROM. So this is what we have to do now. Let me start by giving you a global view of this program. So first we have the header where we are including all the frameworks needed for this main program and also needed for the program that is going to be doing the serial transfer between the microcontroller and the hyper terminal in a laptop. Next we have a routine that is going to initialize the EEPROM. Then we have another routine, one which is going to write, and then we have an additional routine which is going to be doing the reading. Next we have the main program where we're going to initialize whatever needs to be initialized, and we're going to perform the reading, the writing, and all the serial transfer for the display. So let's get into the details. So let's start with the init EEPROM routine. This routine is going to be used to select the mode that we want to use for the transfer. So in this case we're going to use the erase and write in one operation mode, which is known as the atomic operation mode, and that's what these two lines of code will do. That's setting up the correct bits in the register to get a atomic operations. Next we have the EEPROM write operations. The inputs to these routines are two. One is the address where the data is going to be stored, and next we have the actual data to be stored. So the first thing we do is we go through a while which is going to keep going until all the previous write have been completed. Next we load the address into the EEAR register. Following that, we load the data into the EEDR register. Now, for the transaction to occur, meaning that the data gets stored in a particular address, there are two lines of codes that we need to set. One is the EEPROM master write enable, and the next one is the EEPROM write enable. Now after those two lines of code get performed, the data get immediately stored in the memory. So now let's look at the EEPROM read. The inputs to this routine will be the EEPROM address from where we want to read the data. So as usual, the first statement is a while, which is going to ensure that all the previous reads or writes get completed before we do anything. And that's by checking the flag. Next, what we do is we store the EE address in the EEAR register. And finally, we enable the EE master read enable register. Once we perform this line of code, the data will be immediately loaded into the EEDR register, and the value that gets loaded, it gets returned to the calling program. Next comes the main program. Let's see what the main program does. So first initializes the UART interface that was required by the program that is going to do all the serial transfer between the microcontroller and the hyper terminal in the laptop. Next, we initialize the EEPROM. Now the next step is we clear the screen on the hyper terminal, and we send the command hello world, and then we jump 2 lines. So let's see what this looks like. So here we have, this is the hyper terminal that would be in the laptop. So we wrote the hello world message, and then we jump 2 lines. That's right here. Next, we write input values and go to the next line. So let's see what that looks like. So we write the input values, and then we go to this line. Now what we're going to do here is a number of write statements. So we're going to write to the memory 1, A, B, C, D, E, and 3, FF. And the data we're going to write into those addresses are 00, AA, BB, CC, DD, EE, and 00 again. Those are all hex values. So once we completed this writing into memory callouts, next hit, what we're going to do is we're going to display in the hyper terminal in the laptop the data that we have stored. So the data, we're going to display the 00, AA, BB, CC, DD, EE, and 00 in hex. And to do that, of course, we use the unsigned integer on base 16. So what gets displayed is in base 16. So let's look at it. So here we have what we displayed: 00, AA, BB, CC, DD, EE, and 00. Those are the hex values. So we store the data, this data. We display the data that we had to store. So next, what we're going to do is we're going to jump 2 lines on the hyper terminal, and then we're going to put the following. We're going to print read values, and then we're going to the next line. So we have here read values, and then we go to the next line. And finally, what we're doing in these lines is we're going to read from EEPROM read from memory 1, 08, 0B, 0C, 0D, 0E, and 3FF, which are the locations where we store the 0, AA, BB, CC, DD, EE, and 00. So we're going to read from those locations, and then the result of the read is going to be displayed on the hyper terminal. That's why I use the routine serial uint base 16. So let's look at it. So it printed the values 00, AA, BB, CC, DD, EE, and 0. Those are the values that it read from the memory, and it matches what we inputted. So this program, it actually was capable of writing stuff into the EEPROM, and then was able to read it. And to validate what was going on, we printed all that information in a hyper terminal. So this pretty much completes this example. So let's keep going to the next section of my presentation. So what was left was the summary. So today I gave you some background on the EEPROM. I developed the framework and we went through a sample program. So I hope you've enjoyed this presentation. Hope to see you in the next one, and thank you very much.